Okay. Sunny, we go ahead, right?
Yes, sir.
Okay. Yeah. Okay. Good afternoon, everybody. Welcome to Machine Learning for Material Sciences again. For the next two classes, what we'll be doing is we'll be covering some of the basics of machine learning per se. We'll not divulge into algorithms straight away. There'll be some parts of algorithms this class as well as the next class. But we'll formally start covering algorithms from, let's say, two classes after today. Uh, but these all are important because this should tell you the main reason where I think like entire algorithm process has to follow, like anywhere in your domain, let's say material science or any other domain, is majorly to solve the question like, do you actually need machine learning to solve this problem? Yeah. And hopefully today's class and the next class will give you some insight or probably, okay, maybe this is a machine learning problem. Yeah. Okay. So with that, I think yesterday's class we covered a bunch about what we are expecting in this course to cover and what we are definitely not going to explore in this course. And I gave you a brief intro, and Professor Sen talked about how it has been affecting, like machine learning has been affecting material science as such, and some of the data sets, repositories that he has told, and what we will be trying to cover. And I also talked about some of the course syllabus from machine learning side and what is expected in terms of grading and all. And then we also covered some parts of AI, right? Two major thing from key takeaway from the AI part was like AI is super huge, but the definition comes down to very simple thing. Uh, and can you design something, you or something not human, let's say artificial, which can solve the problem as good as a human does? Yes. Uh, if it is better, it is super intelligence. If it does many tasks together, it is general. If it does only one task as good as a human does, then it's narrow. And we discussed some on predictive and generative. That's not the main focus though. But the major point that I highlighted yesterday that was like AI is big, and out of that, a small chunk is like machine learning, right? And probably that bigger chunk that is left out, some of the things I told you, like naively solving all the possible paths, is there, or if somebody could actually replicate the entire human brain, let's say, yes, if somebody could just replicate human brain, yeah, then we don't need to, we need some kind of, but we don't might not need to train on this very large examples, right? So for example, like swimming as a skill to learn, right? So even if you, for example, like a baby understands that if it is in water, it has to throw hands around and legs around. Somehow that information has been passed through, yeah, through some or the other way. But today and from now on forward, we will be only focusing on machine learning part of AI. Yes. And whenever AI is being talked about, specifically, we'll be talking about machine learning as a whole. Yes. Now, so then we need to define, like, for example, what would be machine learning? Yes. At a very basic level, of course, like machine learning would be about predicting the future based on past. Yes. And for example, let's say we want to know how one of you, let's say, will like a movie which you haven't seen already, right? So, but we need some information to tell that. So either we know the ratings of your that you have given for all the past movies that you have seen. So some information we have. And the future prediction has to be based on your rating, of course, and also the category of the movie. Let's say it is a drama, it's a documentary, it's an action movie, or probably the language of the movie, or the director, or the actors, or maybe the production company. Some people have affiliation to that. And so, in general, what we want to do is we want to make some guess, of course. It's That's why there is no science in machine learning yet, probably. But we want to do some guesses about something that we don't know, yeah, something unobserved, based on already observed properties of that particular object. Yes. That means, for example, if you tell me a movie, you have to give me some more information about it, right? You cannot just tell me, okay, movie, let's say Coolie is coming. Do you like it? You have to tell me the actors or the directors, or like, is it a drama? Is it an action? You have to tell me a bunch of stuff about it, right? So you have to make some guesses about some unobserved property, that is the rating, let's say, but based on some observed properties that you have seen before. Yes. But the guesses cannot be super random. The guesses has to be some of the informed, and that information comes from the observed properties of that object. Yeah. So at the core, then machine learning becomes predicting the future from the past. And some of the examples are, for example, like, will you like a movie that you haven't seen? Can you recommend courses for students that you probably they have not taken yet? A very fine example, of course, your spam emails, they're detected without knowledge. Google does it now. And stock prices, rating properties of materials. Yes. So again, making informed guesses about some unobserved properties based on observed properties. Yes. Uh, and all the slides, we will put it on the website. So not in that, but any middle points that we have missed, you can take a note of it. Not an issue. Okay. So now that is done, but the definition of machine learning will keep on changing as we go through the course. So take the definitions with like on a course level. Don't take it to be like super fine. Yeah. Now that we have this, now the next question is like, what is learning, right? So we have to ask that question, what is learning? There is a nice example I keep on taking. So for example, let's say all of you have now begun taking a course in, let's say, machine learning for material sciences, right? At the end, we will expect that you have learned all about this topic, all at least like, the most about this topic, right? So, what is the way that I can tell you have learned the most about in this topic? Any guesses you can write in the chat? Like, what would be a way that I can tell that you have actually learned the topic? Let's say machine learning for material sciences. Any quick chats, maybe? Oh, sorry, I cannot see YouTube. Yeah, so Shubhankar is fine, I think. Oh, sorry, somebody has my name exactly. Uh, Fine. Shubhankar is correct. So, exam is one of the ways we figure it out on how to judge somebody. Fortunate or unfortunate, that's the way it has been. So, the way for us is that we'll give you an exam at the end with the projects count them as exam also. And if you do well on the exam, we'll understand that you have learned the course. Yes. Now, so from learning, we have now shifted to the definition of exam. So we understand that what does it mean to learn. So if somebody does well on the exam, then it we understand that is learning. And then now we have come to the point of exam, then we have to ask the question like, what does it mean to have a exam? That's it. Or what makes a reasonable exam? Yes. So now, for example, let's say I will talk about entire course on semester on machine learning, right? But then I will give you an exam on, let's say, history of Odisha. Yes. Like even if you score 0 or even if you score 100, does it matter? Like, can I still tell you have learned this course? It's hard, right? So it's definitely not a representative, right? So I have taught you machine learning and then I'm asking you on history of Odisha. If some people might score 100, but some people might score 0. None of them are representative of your learning, right? The other way around to look at it is basically, for example, let's say if the exam only asks question on exactly what I have taught, like whatever is on the slide comes exactly in your question paper. Yes. Would that be a great idea to judge, like design an exam? Again, no, right? Specifically because you can just remember and then just come up with that. Yes. So if I give you the exam based on the notes that have like or the slides that exactly that has been taught in the class or covered in the class, then that also is not learning. But if I give you an exam that is completely separate, like completely different from what has been taught, so if it doesn't matter what you score in that exam, that also does not count as learning, right? So where are we? So where the exam matches the notes, that's called memorization. Let's say even if you score high. And if you are absolutely like you're scoring super nice on exam, which is like very far off, like history of Odisha versus machine learning that I've taught, and if you score really well, then you are probably on the oracle category, right? So there is no learning per se, you just know everything. That's the answer for it, right? And so because these two and then these two have no relation with learning. So learning will lie somewhere in the middle, right? So in the middle is basically, so that middle path is called, there's a nice term that we have, it's called generalization. Yes. That means, do you have the ability that given some of the notes that we have covered or some of the examples that you have covered in this course, use them, understand the patterns from them, and but you answer new questions that are put in the exam, but that are related to the questions in the exam. Matlab related questions in the exam itself. Yes. So generalization is the like probably the core concept behind machine learning. So eventually memorization is not. And then being oracle is also not the answer. Somewhere in the middle, that is called generalization. The questions will be new, but it will be based on the initial notes that we have covered. Yes, fine. Now we can be a little bit more particular
Sir,
on this example. Yeah,
is it like
please.
extrapolating the data or it is something more?
So
Uh,
yeah, okay. So extrapolating is one of the ways. I'm not saying that is not ML. Of course, like if extrapolation depends on other examples, then it is sure. Then it would be learning.
okay,
Yes.
okay,
Yeah. So definition, I hope it is becoming clear, right? So learning would be based on exam. Then if you have to do good on exam, the exam here is, for example, I have given you some past few records and you are trying to predict for the next one, which is basically, let's say for you is an extrapolation exercise. If you do well in that exam, then I would assume that whatever model or you yourself, if you can extrapolate well, then you have learned, right? But you are not a machine. So you, like if a machine does that really well, then it is a machine learning, specifically algorithms or robots. Yes. Okay. And okay, so we go ahead. Just to based on like again going through the example, a little bit more maybe with numbers example. So let's say we have a course recommendation, right? So if people want to come, they want to take courses, and students have rated their courses from -2 to +2. Yes. And we have to predict how much, let's say, a person like Alice will rate a course called algorithms. Yes. So the questions can be like very unfair questions will be, I can ask Alice like, will she like history of pottery or not? I have to guess, like a course recommendation software has to guess. History of pottery is like a completely different course, right? So, and will Alice like an AI course? Alice has already taken a course in AI. So she will just tell, okay, I have liked it earlier, so I like it again. So the previous one was like very different. So no training data is available. And the otherwise AI is just a recall. So those do not count in terms of learning. But a fair question or a fair exam here would be like, can will Alice or how much Alice will like machine learning course? Yes. So that can be based on examples of machine learning related course that she has taken, like let's say AI or like computer science or the courses she has taken. Yes. Okay. Now with that, we'll go ahead a little bit further. So I hope that is understood relatively for now. The next is like the learning framework. So based on what we have just known now, so we are trying to guess some unobserved properties from the observed properties. Yes, and that guess has to be an informed guess. And the more common example of the entire pipeline or the framework that you will see is some like looks something similar. So that will have something called training phase. Training phase will have something called a training data. It will have which will basically contain examples of the previous past history, and that all those will be fed to a learning algorithm, right? And the learning algorithm basically eventually finds the function f. Yes, this entire process is called induction. You will hear the word induction, inductive a lot of times in at least in like next 2 or 3 classes. So the idea is like if you have learned something, like I hope you understand the inductive proof. Like for example, we say base case is true till k this is true, then prove the k plus one. It's more on the similar front. So like let's say we have understood some of the examples in the past. We want to predict the next one. Yes. So inductive and induction will come a lot of times. That word. Yes. So then whatever the training examples are there, based on that, there is a learning algorithm. We'll be focusing majority in the learning algorithm point. At the end of that, that generates a function f. Yes. Uh, and then the f is used to predict some labels. The labels will come back and will define, but on a test set. And test set is something that we have never seen. And if you go back to the analogy that we had before, so the notes that we had or the slides that we had that would go into training, the exam that we had, the questions would be a test. And of course, students are not allowed to see the test beforehand, right? So the F will never see the test before prediction. Yes. So the same principle applies. And how do we judge if let's say the machine has learned really well, if it does really well on the test example or the test exam? Yes. So just to repeat, the goal of the inductive machine learning task would be like to take some training data, use it to induce a function f, right? This function f will be evaluated on a test data which is never seen before. And we will tell the machine learning algorithm has learned or is successful based on whatever it has performed on the test example. Yes. Okay. I hope things are fine. So, of course, as we go ahead, there'll be multiple such definitions of machine learning. Again, so machine learning will be a subfield of AI. I told you subfield. And we have to learn from the data itself. We have to recognize some patterns in the data that was present. We have to make some decisions, some actions. And we have to make sure that it is not explicitly programmed to do so. Yes. Uh, Now, the next step is like, then what are the things that are necessary for making the machine learn? Yes. So there are two important things. There is one is the data set and the algorithm. I talked about the third one previously, like compute. Compute is more in terms of efficiency rather than like need per se. But it has become a need because models have become larger, data set has become larger. So without large compute, you won't have. But majorly data set and algorithm which decide like how machines learn. Yes. So data set will be collection of examples and algorithm will be our step-by-step procedure on how machines will learn. Yes. So the algorithms eventually will induce a model from the data set and it will use that particular induced model to solve and predict. Yes. Now we'll move on to types of machine learning, some types, and there are a few types I think processing also talked in the first class. So initial types are like supervised learning, unsupervised learning, semi-supervised, and reinforcement learning. Majority, would you have some idea on top of it? We'll be just building on top of that, of course, yes. So the first part is like supervised learning, let's say. And supervised learning is, okay, so just before that, so types of machine learning will define multiple times. So this type of learning on supervised, unsupervised, semi-supervised, and reinforcement learning all depends on the output, like the properties of the output data, okay? Or the outputs that we're expecting. There will be others that some other property of the output, yes. So for the supervised learning, this is what we have. So the data set will be a collection of labeled examples. So this notation, I will try to keep it continuous even if you don't see it. Please try to relate it as just basically a collection of xi and yi, and I, let's say, represents the example, the index of that particular example, and we have n examples here. Yes, and your xi, sorry for the notation a bit, but xi, assume it's a feature vector and it contains like a d-dimensional feature vector. That means it is a vector of collection of, let's say, d elements. Yes, and yi will be a label. Yes, so all these types of supervised, unsupervised, semi-supervised reinforcement, generally this type of machine learning has come from the classification based on the yi being the having a label or not. Yes. And in the, like for example, let's say X could be a person, and the feature could be like could be height, second feature could be weight, and third feature could be gender, and so on and so forth. Yes. And similarly for the materials, I think you can, if you can give a feature vector, it will have like properties of materials like the band gap, other things. Yes. Probably the constituents also, that also could be given. Yeah. And the label would be like, for example, let's say magnetic property. If you have, I'm not super into material science, but like those properties, let's say. Yes. And label I is generally either could be a, like a real number, or it could be a, like a category of elements. If it is a category of elements, then that is called, and if it is finite, then it will be called classes. Yes. And otherwise, it could be just a real number. For example, temperature could be just real numbers, they're continuous in domain. But if I have to predict the weather to be sunny, cloudy, or rainy, then that becomes like a limited set of classes from which a label can be picked. Yes. And one of the examples would be like if the email messages can be spam or not spam. Yes. And so the goal is to produce a model that takes a feature vector as input and produces the output as label. Yes. Super simple, but this is the most widely used kind of learning. Yes. So you have been given a feature vector X, which constitutes of many small elements of 2-dimension D, let's say, and you have to predict a label at the end. Yes. The next would be unsupervised learning, and here you have exactly the one that was present. I told like the yi, which defines the yi is missing. What you have is just examples of xi, which is again a d-dimensional vector feature that defines a particular object, but you don't have any label associated with it. Yes. And so what can we do with it? Specifically, like we can find hidden patterns, we can find some structure or representation in data. Yes. And for some of the examples I written here, some of the examples are like clustering. We can group similar items together. We don't need to know what they mean, but similar items can be grouped together. Another problem is dimensional reduction. For example, if you have just too many feature vectors you have, but maybe you think that that either that does not fit into your compute, or maybe not all of them are required. Yes. Then you could compress the data. And there is a density estimation also. Then there is outlier detection. Yes. If like outlier detection would be like a threat analysis, for example, like for example, a lot of networking data you are transferring from your mobile device, let's say you are interacting with, but your computer runs outlier detection, anomaly detection software on it. Anything it finds odd, it will flag it. For example, your captcha and reCAPTCHA all you have. So Google keeps a track of your how you move the mouse and what websites you visit. Based on that, it tracks, right? And if you do anything that is not normal in the terms of not usual, continue to past. So even if it does not have a label what is harmful, it can just flag that it is unusual. I don't care what it is. It could be harmful, it could be useful, it will just flag. Yes. And credit card companies also use that similar thing. So if you do a shopping of a particular object at a very different location, they will flag it. Yes. The problem here, of course, is that we don't know what is correct, right? So even if I group together items based on some similarity, what does that mean? Does that group actually mean anything or not? Yes. So we don't have any knowledge base on that. Fine. So that is unsupervised. Supervised is again, we have the input feature vector, which describes the observable properties of the object, and then we have to predict y. And here we don't have any y to predict. In the data itself, we don't have, as well as we cannot predict y. Yes, so the question is not even that. But again, as you can see, clustering, dimension reduction, density estimation, and outlier detection, all of these are very useful functions. Yes. Now the next thing, the numbering is a little bit off, but I will first discuss reinforcement learning. So this has been super useful in very recently. So here what happens is there is you can talk about a system or like a expert system. We can call it as an agent. And basically the agent will learn itself through the interaction of the environment. Yes. So like an agent would be there, it will go through the environment, and whenever it is present in an environment, that will be the state of the environment. Whatever it perceives, it will be the state. For example, if I am in solving a puzzle, then if I can see the boundaries of the walls, that would be a state. Yes. And at every state, I will have certain set of actions that I can execute. Yes. And each action will give me some reward, and that reward will vary on the state as well as on the action taken. Yeah, the same action might not give the same reward at a different state, and so on and so forth. And also, action will help me move to another state. We can also take an action which keeps me there also. Yes, like sometimes we play games and we do a pass also, right? So we can remain in the same state, but the environment around us might change. Yes. Now, what is the goal? The goal is basically we have to design a policy. We have to find a policy. Yes. Or we have to induce a policy now, which will give us like a collection of actions that we have to take, and which will finally help us winning the thing or gathering the maximum cumulative reward. Yes. And reinforcement learning is like generally used for long-term decision making, where, for example, let's say game playing, robotics is there, autonomous driving, if you can see. Yes. If you look at, like, if you reduce the mumbo jumbo in the terms in the particular whatever I spoke about, if you see, look at this reinforcement learning and supervised learning, it looks very oddly similar, except there's a minor tiny difference. So here we give the feature vector as well as the label. Here we give the feature vector. We can also extend the feature vector to contain the environment as well. And we can also have like the yi could be the reward that we get at the end. But what's the tiny difference in like reinforcement learning and the supervised learning? The only difference here would be the reward that you get does not mean like a particular level. For example, let's say in a game, let's say, or this maze problem you're playing. So if I take a step, yes, I don't immediately win or lose. And generally in supervised learning, given a set of values, I can either win or lose. But here, for example, I have to either take all the steps and then declare my win or loss. But if I take a very particular step, I don't have a notion of win or loss. There is no correction associated with it. We have some expected reward, but that expected reward is calculated through a lot of other things, but I don't have a win or loss at that particular state, yes, or that particular action. So I can only win at the end, right? So I have a winning notion at the end where I can do corrections. So I can correct my steps only through the notion that I do at the end with a win or loss. For example, this maze, I will take a bunch of steps but I don't reach at the end, then it's bad. If I take this similar number of bunch of steps but I win, then that makes sense, right? So at the end is what decides. So that would be reinforcement learning, right? So generally long-term tasks are reinforcement learning, and super useful nowadays. Super useful. You can ask like, why is it super useful now and not earlier? This is a super expensive algorithm. Now there's because of compute, and we have seen use cases where it can be useful. So this has become super useful now. But training it is really, really hard. And in this course, we'll not be covering reinforcement learning as such. The last thing, that the property based on the yi. So if you can observe, like all the things are based on the yi, right? So supervised learning has yi, unsupervised does not have yi, reinforcement learning has yi, but towards the end does not have middle steps yi. And semi-supervised is the somewhere in between the supervised and saying supervised, unsupervised learning. So here what you have is both labeled data as well as unlabeled data. Labeled data means you have xi as well as yi, the label associated with it. Like we have, for example, man with a lot of properties, and the label is there. Like let's say he belongs to neither. That's it. Yeah. And we have a bunch of properties of other students, but we cannot say if they belong to neither or not. That would be unlabeled. Yes. And so, yeah. Hello. Is there a question? Sorry. Okay. Uh, I'll continue. So now what happens? In this, for example, we have a lot of unlabeled examples, and then we have a few labeled examples. Yes. Uh, but what can we do with unlabeled thing? So I think the information comes from rather from unsupervised learning as well. So instead of asking questions to a bunch of unlabeled, if we can, like, for example, let's say take a lot of unlabeled examples, we can group them together because unsupervised learning can happen. And then if we find some labeled examples in each of the clusters, then that solves the purpose. I think we can ask questions similarly to a group, right? So that could be the way. And why is this semi-supervised learning very useful? Because in the real world, majorly whatever you will get is on like this state. You will have some labeled and a lot of unlabeled. Yes. And one of the examples is the chest X-rays. During COVID, it became a little bit. We had a lot of chest X-ray data, but we did not know what was COVID positive and what was not COVID positive data set. Like X-ray images, for example. So this is super useful in that sense. Yes. But also this can can be a little bit misleading. There was one area where, for example, there were a lot of X-ray images we had got, and then what happens is if we try to group them together, what happens is it did on the X-rays. If you see on the top right or somewhere, they write the, let's say, hospital name where the X-rays were taken. Yes. And based on that, what happened is the unsupervised learning algorithm, let's say, group them together based on the hospital name rather than grouping them based on the what it looked on the X-rays for those lungs, right? That's not useful, right? Then we tried, okay, if one person from this particular hospital is COVID positive, or another person is not COVID positive from another hospital, then we are trying to make assumptions which are not correct, right? We'll tag, okay, like probably all of these X-ray images are coming from that hospital and not COVID positive. It should not be like that, right? So we have to be very careful in doing this, majorly because it lacks data, so it lacks labeling information. Yes. I hope that is clear. And there are many other things. So, for example, web page classification, few manually labeled, millions are unlabeled. Medical diagnosis, again, few expert labeled, many patient records are there, but only few are like we tell exactly what they are. Speech recognition, again, like YouTube videos, there will be a bunch of them, but like, for example, translation for them, or like say we don't have them, like transcribed audio is very less. Image classification, we have thousands of images. What do they mean? We have no idea. Yes. And where it is used, we will talk about data distribution and distance boundaries a little bit later as we go ahead. And I told you the challenge, how do you use unlabeled data without introducing noise? Noise is the one that I talked about, the hospital name on the X-ray. That was the noise, let's say. So how do you traverse through it? Yeah. Fine. So this was classification was based on the availability of label on the output. Like if we have a label to predict both in the input as well as the output. And the next is basically what we talked about is basically if your yi becomes continuous like temperature, or it becomes like classes in terms of like it's a finite set of elements. Yes. So what we have is, let's say, regression we have, which is basically we have to predict real value numbers, stock prices, exam scores, house prices. And how do we measure the error? Distance from the true value. Yes. So like if the temperature was 37, we predicted 38. That's the error we have. Then we have binary classification. Let's say we predict yes or no, and predict positive or negative, cloudy or sunny. Yeah. Then how do we measure error in binary classification? We predict wrong. So it was cloudy, we predicted sunny. It was sunny, we predicted cloudy. Yes. So it is regression, then binary classification, then we have multi-class classification, just having more number of classes, multi-class classification. And we have to, so one of the important things in multi-class classification is that we have to make sure that all mistakes are equally bad. Sorry. For example, like even if cloudy and rainy, they look close to each other, still me predicting like cloudy or like sunny shouldn't be valued higher or lower. Yes, so both are equally bad. Yes. And the last kind of classification of machine learning algorithm per se would be like a ranking. So you can still take it as a classification task where you're predicting classes, but here the position matters, or the what would I say, the output labels have some correlation among each other, right? So for example, search results like the first, second, third and fourth search results are very important, right? For Google, ChatGPT, let's say, what answer does it give? All these are super important, right? What comes first? And course recommendation, for example, what of the good course, it cannot come on 10th. Just because it is in top 10 doesn't solve it. It has to come on first. Yes. And error, like what is the position it's supposed to be and what is. Yes. The major important part here, you have to understand that uh, before like the unsupervised, unsupervised, semi-supervised reinforcement, that matters based on the availability of labels. And then regression, classification and ranking and multi-class classification, let's say all this matter when the output, the definition of output changes from temporary to, let's say, like, sorry, continuous to classes and ranking. Yes. But you also have to be a little bit more careful. For example, let's say regression, 38 is a wrong answer compared to 37 if I'm predicting temperature. But if we use the same error method to calculate, like the sunny and rainy, even if a tiny, you cannot say that is a tiny mistake, right? That's a huge mistake. Yes. So the tiny mistakes in binary classification or multi-class classifications are super huge. The tiny mistakes in regression we can assume. If you predicted 37 and 37.5, we can probably get into adjusted range. Yes. Fine. And so these are again just examples. We'll just take it ahead. So what do we have? So machine learning again, just a repetition of what we have done. So machine learning, how do we define learning? Learning is based on the exam. What is a reasonable exam that we define? It cannot be exactly same as node. It cannot be far away. It has to be something closer but new. Yes. And then we discussed on types of machine learning that we have. Yes. And we discussed on the inductive way to do so. And so what is the machine learning pipeline again? So we have training data, which are past examples. We have learning algorithm, which is generally trying to find patterns and inducing the model F. Once we find F, we can do predictions. We do predictions not on random stuff, rather we do predictions on the test data. And then whatever we predict, based on that, we evaluate. Yes. So train, test, and make sure that our algorithm never sees the test data. Yes. Fine. And we say it has learned really well if it has performed well on the test data itself. Yes. Okay. So now let's go ahead and we'll go through an example. We'll discuss on how supervised learning works in a bit more in a verbose manner rather than going into a little bit more depth. So one example, let's say we can do this example, consider this example like where we want to recognize spam emails, right? And if you have if you have opened any email account ever, you have received a spam message. And one of the some examples are, let's say, winning money, free offer, doing this, doing that. Yes. So what we can do, or earlier people used to do, let's say, they used to write explicit rules for it. Uh, Sorry, is there a question? Okay. Um, okay, I'm hearing an echo. If somebody has turned on the mic, if okay, thanks. Yeah, fine. Um, so we can write like explicit rules. If there is a word called free offer, uh, we can mark it as spam. But what if you received an email from, let's say, some company, Flipkart, Amazon, or Lenskart, let's say, which actually offers you a free offer, then that goes into spam, right? So what is happening is that like the eventually you will find out, okay, if the email comes from Flipkart, what if Flipkart change something to, let's say, Independence Day at the rate Flipkart or random something offer, then that is a true email. But again, so what eventually happens, as we discussed last class, so the number of this rules that come up, they become just too many, or there just becomes too complex, right? And or for example, if somebody put like free has to be in small letters, somebody puts capital free, then it is okay. Might be easy to bypass. Like one of the examples, like free, if there is one more e in it and we explicitly put like free to be the keyword, then what do we do? Yes. uh, and also, like, if we put explicitly, then we don't also match whatever the newer spam emails are coming, right? There's no learning per se. Yes. And generalization is missing because the only thing that we are doing is we are remembering whatever happened in the past, we are putting it. So there is no generalization happening, like we are not learning anything to answer any new questions. Yes. So what do we do? So we can start because we have some information, that is the email will have some words, and of course we can put some labels on top of it, that is the spam or non-spam. That means we have xi and yi both, so that becomes into the stack of supervised learning, right? And we know this is a spam or a non-spam, so we understand we have to predict categories rather than continuous, so we'll be using a supervised learning plus a binary classification, right? So based on whatever we have covered in the previous slides, so that's the pipeline. Yes. So we want to build a system that automatically detects spam emails, right? And we chose this example, of course, this is a practical example, and we will show how this relates to it. Yeah. So how do we start? Yes. So this will start by, first we have to gather a bunch of data, right? So the data has to be, because it's a supervised learning approach, so the data has to be in a pair form, like the input and output. And input could be anything, like for example, let's say it could be the messages, it could be the pictures, it could be the, for example, material properties, it could be anything. But for here, for example, it could be messages or pictures, let's say, yeah, because these are emails. And outputs are, of course, here it's spam or on spam, yes. And how many we can gather? Let's say we gather 10,000 email examples, and we know that there's spam or non-spam. And now the point is, these are still email messages, and if you see the definition of supervised, it wants to find the inputs in form of vectors, right? And a vector has to be in terms of collection of something up to a dimension, let's say d, that d has to be fixed per now. Yes. So now the first goal is, we did the data collection. We did 10,000 messages. We tagged them into each messages into spam and non-spam. So the label is fixed, but the messages are there, but the messages are not in the form of a vector. Yes. Now we have to convert into, let's say, a vector. Yes. So how do we do this? Now, if we have to convert an email message into a vector form, so one common way, and there are much fancier ways nowadays, but one common way is something called a bag of words. If you have heard about this one, uh, so bag of words works like this. So what we can do is, we can take a vocabulary of, let's say, English words. So let's say there are many words like the, free, cat, dog, and all this stuff. It's a vocabulary of English words. Yes. And we can pick the size of this vocabulary. Let's say we take 20,000 words of commonly used English words, and then we will tag them in particular order. And then we will say the first value will be 1 or 0 if that particular word is present in the email or not, right? So we are not going ahead with any frequency. We are just saying that if A is the first word in the featured vector we have, if A is the first word, if A is present in the email, we'll just mark it as 1. If D is not present in the email, we'll mark it as 0. Same with cat, dog, free, and win money, and so on and so forth. So the first step is to convert the entire email message into a feature vector, right? So will create a dimension of 20,000. We'll keep on putting 1, 0, 1, 0, 1, 0, 1, 0 based on their presence in the email messages for every email message that we have got, right? So now each email becomes a 20,000 dimensional vector, and we have 10,000 of such. Now, if you understand our data set from 10,000 emails have increased to 10,000 cross 20,000 size, yes. And what is the usefulness of this one? This is computers play very nice with numbers. So what we can have is basically we have something called a machine readable input data. Yes, and output is already in a machine readable form because it's a spam and non-spam. We can tell spam like spam to be 1, non-spam to be 0. Yes, and it's super easy, right? Here we have to be a little bit more careful. Sometimes what happens is some algorithms specifically want you to design this binary classification labeling done to be in a particular way. One of the example is support vector machine, which expects it to be like, let's say, -1 to 0, like -1 and +1. And you can also have 0 and 1, like logistic regression. There are a few other algorithms which explicitly want it to be 0 and 1, and so on. Yes. So now what we did, so first we gathered data, 10,000 emails, message or text, assume text for now, then we converted into vectors. Vectors are called features. We'll keep on defining those features continuously as it comes again in more depth. Why are features? They're called features per se. But again, these are features of the particular email, so that's why they're called features. Each particular individual word describes some feature of the email. Yes. And then we also, so this one converting to a feature of dimension 20,000 help us to make it machine readable. And we also made the labels to be machine readable. The next step is we have to learn now. Now, all of them are in machine readable format. So we have data set, we have 10,000 feature vectors, 20,000 dimension, labels are like +1 and -1. Let's say the algorithm that we're using is support vector machine. And we have to use this algorithm to find or induce a function f, and then we can use the function f to classify future emails to be spam and non-spam. Yes. Now, what does SVM do? This particular algorithm basically what it does is puts all the feature vectors that we have in a 20,000 dimensional space. Yes. Now you have to, I hope like everybody has some background like on this dimensions and vectors. So like each point here is a point, like each email becomes a point in a 20,000 dimensional space based on the values of 1 and zeros, whatever you put for the particular column, let's say. Yeah? And then what it tries to find out, it tries to find out the hyperplane that can basically cut through the entire 20,000 dimensional space, where on one side there will be a bunch of like spam points and the other side will be non-spam points. Yes, points here refer to emails, of course. Yes. And that particular hyperplane that is there, which basically cuts into two halves where everything is on one side and like one particular class is on one side, other one, that will be called distant boundary. It's called distant boundary because the next time the new email comes, we'll basically take that point and put it on the 20,000 dimensional space. If it falls above or below, based on that, we can take a call. And that boundary basically decides for us if it is a spam or non-spam. Yes. Okay. So now this is just like a view of stuff. This is not SVM per se. We cannot show 20,000 on our picture, of course. So I've just converted them to like a two-dimensional space. You have, let's say, assume one of them to be spam, the other one to be non-spam. And our goal is to find a line here because the two-dimensional space, a line that cuts through and then decides, right? So of course I can create any random line, right? So this one has no point, right? So it has to be a line which basically separates. So this option one, creating a random hyperplane, does not work. Yes. Then there is a next point, right? I can put this a green line in between them. If you see, look at the green line, it stays somewhere in the middle, and it can separate both of them well, right? So anything that is below the green line, like if you see to the left hand side of the green line becomes blue, anything that is on the right hand side becomes orange. Yes, or spam or not spam, and we can easily do so. But why this one is not a great idea to do so? Any observations on chat? Like this is one way to do, like we can have another line, for example, it's a green line that also distributes between the pink, like the orange and the blue. But any reactions from the audience, like why this is not a good idea? Fine, I'll keep on waiting. If there comes, then we'll keep some time at the end really to go through. And assume like this, any added point may put you in trouble. Not necessary. So any added point, let's say, like any added point could put me in trouble anyways if it confuses. But yes, in some directions, yes. If there is a new point, it might put in trouble. But there are more conceptual issues with this particular diagram. But anyways, we'll go ahead. As you please keep on posting. I'm looking at the chats, not an issue. The next option that we have is we can put something like this. So initial option was to put any hyperplane. That does not work. We can put something in the middle. It relatively looks all right, but like the support vector algorithm says this one is not correct, let's say. And we can also do this, right? Somewhere we'll also put another green line. Let's say this is a new version of the distance boundary, which is in between. Again, this separates very well between orange and the blue. But this is also not a good idea. Why this is not a good idea? But the answer is there in the picture, of course. Okay. Line is not unique. That is true. Line is not unique, but like decision boundary need not be unique in that sense. Uniqueness, for example, finding analytical solution is never. Okay, if it's in the scope, but uniqueness probably is not maximally separated. That is true, but why is not? Okay, most of you are writing stuff. I'm looking at. If you can keep on posting. So majorly, one of the nice examples too. For example, the new point. Let's say what Rahul is saying is probably it is correct. But the new point, if it comes, if you see the cross, it looks very close to the orange rather than the blue. But because of the distance boundary we have put in green, it looks like as if it should have belonged to orange, but now it is in blue because of our distance boundary choice. Yes. So this leads to the support vector machine algorithm, which one basically says that we need to choose a margin. Margin is basically this green line. I'll talk about it a bit more. Which is need to choose a distance boundary which has the largest margin, right? So I will jump to the example here, like the figure, and then I'll come back. So if you look at the blue examples and the orange examples, and if you look at the line here, this particular red line here is basically what does have the maximum margin. And here margin is basically the distance between from this to the nearest point of one of the classes, right? Or both of the classes. So the distance from the red line to the line with the, let's say, the wx minus b1 and wx minus b minus 1, to the both the lines, it has to have the maximum value, right? So if you calculate mathematically, that will be like 1 over norm of w. Yes. And eventually what we have to do through this, we have to, the SVM algorithm particularly states that we would eventually minimize this norm of w given some constraints. The constraints I will come and discuss, but we have to find this particular decision boundary that will basically maximize the margin. Yes. Fine. And why is this a good solution from SVM point of view? This basically helps us avoid this particular condition, right? So, for example, let's say if this particular point comes, this looks closer to orange, then in this particular line, if it is closer to orange, it stays closer to orange, and we can tell it so. Yeah? And there are a few other terminologies associated with support vector machine. This is just an initial idea on how supervised machine learning works to solve a particular problem. Yeah. Uh, okay. So now the decision boundary that we have here has, like, it is wx minus b is equal to 0, let's say, for, and then we can add the bias b basically allows us to shift around the axis. And the constraints that we have is basically every blue point or let's say everything that is plus 1 or that is a span has to lie above the line wx minus b is equal to 1, and everything that is marked as minus 1 has to lie below wx minus b is equal to minus 1 line. So those are the constraints. So the goal is to finally we have to minimize the norm of w, which is equivalent to maximizing the margin given the constraints that uh, wi multiplied by wx minus b is greater than or equal to 1, which is equivalent to those two constants that we just discussed. It's basically wx minus b greater than 1. For all everything that labeled as plus 1, it has to lie above that line, and everything that is below minus 1 has to lie below the line of wx minus b is equal to minus 1. Yes, we'll discuss this in a more detail when SVM actually comes through. Yeah. But for now, let it be. Yeah. And what do we find at the end? At the end, we find the W star and B star. Yes. W star and B star are the optimal values of W and B that we find. And that is basically the induced function F. Yes. And we can use the F now. Basically, we have found already W star and B star based on the constraint, based on our objective. And anytime a new email comes, it has already x with it. So what do? We replace this. If you look at f of x is equal to sine of this, we'll just replace x with the new email's x, and then we'll multiply with w, then we'll subtract the bias, and then we'll find the sign of that. Whatever the sign is, if it is a plus or minus, based on that, we can associate with this category of either span or not span. Yes. Now, with that, of course, there are other things to cover also. Like, for example, what happens if there is an orange on the other side and you cannot do anything? We'll cover all those examples and all those questions in this. And you can also ask questions like, I have a 20,000 dimensional space. I have to find hyperparameter across, like optimize across 20,000 dimensional space. How do I do that? Yes. Those are excellent questions, and there are already excellent solutions to cover those things in particular support vector machines. We will cover them in the future classes when support vector machines actually come. But for now, I hope this is clear, at least in the sense of how, given something today, what is the step to do? You have to first gather data, convert into machine readable format, and hopefully apply an algorithm. And you have to make sure that the algorithm, or you have converted the data set into the format which algorithm can actually view, and that's it. You apply, you get the function f, and then use the function f to now predict for the future. Yes. Excellent. So now, what are the key takeaways for today? So machine learning is equivalent to generalization that we talked about, and there are four main types: supervised, unsupervised, semi-supervised, and reinforcement. We also have regression, classification, and ranking, and of course, the golden rule we can never look at the test data, right? The moment we look at the test data, it becomes training set. Yes. Even if we look at, like for example, the algorithm does not look at, but we look at the test data set, and then we try to design our algorithm to beat the test data set. That again, test data, we as designer of algorithms have already looked at the test data set, so that still becomes a training set, right? Because we are the brains behind the brains of machine learning algorithm. Yes. So if we have seen, algorithm has also seen, we can design some parts of algorithm to perform well on the test. Yes. And error measurement, of course, matters. Different types of algorithms require different types of approaches to solve error measurement. Yes, and the references. These are the references that will continue forever. Like this course will cover, and then that's it for today. And any particular questions, if there are there, I will take it, and then otherwise, yes, we'll end the class. Oh yes, so we definitely cannot look at the YouTube videos while doing. Yeah, sorry on that. If there are any questions, you have to join WebEx. I can check there, but not to YouTube. And about the sharing the private class, well, like on the YouTube, we will try to solve this as Professor Sen has already notified. We will try to get more details, hopefully by this week or early next week for you. Any other questions for today? I hope understanding is clear, like what defines an ML, what defines learning, what defines a good exam, and how do we start with a supervised learning approach. Yes, fine. Okay, I'm assuming there are no more questions. If there are any questions, please keep it for the next class. Thank you all again for joining today. Sorry, somebody asked about the notes. All the slides we will try to put it up on the class website. I hope you have noted the class website. There are no notes per se, matlab as in whatever we cover on the slides. Yes, so we will try to put it up on the course website. Yes. Yeah. Okay. Thanks all. If there are any more questions on this class or the previous class, put it for the next week's class. And 15th is Independence Day. There is no class this Friday. Processing can comment that on the chat also. Like I just want to verify.
Yes, I
Yes.
checked the schedule. So obviously, there are no classes on the Independence Day. So we will have the next class on the 18th. I think it is the 18th, next Monday.
Okay. Fine. See you all then. Yeah. Bye.
Yeah. Okay.